Welcome to the introduction on operating systems on the topic of threads and processes. So here we will outline kind of the basic overview of processes and then look at threads in a little more detail since we have talked about the processes quite a bit. Then we'll talk about scheduling of the processes and all of the possible scheduling algorithms that there are, which are kind of dependent on the application and the system targeted architecture. And finally, we'll look at the issues that arise from trying to schedule multiple processes or threads and how they interact with each other, and conditions for race and synchronization of multiple threads and all processes. So we did talk a lot about processes so far. So we need to kind of look at why do we have multiple processes. So the multiple processes were kind of implemented and came into play as kind of a high utilization of the batch schema that was first proposed for large processing systems. So rather than just running one process at a time, having to enqueue the instructions, run the process, then queue the output, and then analyze the output, the idea was that we can have multiple processes queued up, and when the processor becomes available, we will just swap the processes in and out of the processor, creating this whole notion of multiple programs running at the same time or in parallel. So that's kind of where the modern computers came about, that they can do many things at the same time. They can not only share scarce resources such as a processor or memory, but also some peripheral devices. So parallelism was not really all that prevalent if in a processor system. So we had only one processor. Many processors, they began not to be hyper-threaded, so you could really run only a single process on the processor that had to be swapped out, and then a new process would be swapped back in. So the CPU was running really only one task at a time, and we were not even talking about processors with multiple pipelines architecture. So eventually the multi-programming took over, and the CPUs are now switching very quickly between multiple processes and many more threads. And there's a fine and very distinct difference why we would want to use a process or multi-process computation versus a multi-threaded computation. And that's kind of the driving discussion here through understanding the fine differences between processes and threads. We can also then kind of scale up and talk about which applications would be best implemented as multi-process versus multi-threaded application. So here is a kind of a three views of multi-programming of four programs. So here we have a single program counter, and the processes are being switched by the program counter, basically pointing to the first process, going through the instructions, and then when the processor evicts the process, the eviction place is saved, and the program counter gets updated to the new process, which then executes instructions in a process B. When the B gets evicted, then C gets the program counter gets updated to a process C, and we can see that the program counter kind of goes instruction by instruction until C is done, and then D comes in. Well, program counter is a hardware buffer, so it's actually implemented in a hardware. So many different processors if they have a multiple cores, most likely they also have multiple program counters. So we can actually have multiple processes occupying multiple processors, and each of the processor would have a buffer called program counter that is specific to individual process. So this is, we can look at these processes as being mutually independent, and that would kind of truly allow sequential processes. In reality, this view of multiple program counters is not that different from single counters, because many times we have dozens, if not hundreds, processes running at the same time. So we have multiple processes running on each of the processors, in which case we have to kind of multitask the program counter to be servicing multiple processes, which is not that different than having a process counter dealing with a process switch on a unit processor. So that's why we will not really be talking about these abstract architectures with multiple cores, because when it comes down to it, it's very much similar to a single processor implementation or logic of. And finally, the last plot on the right shows a single program being active at once. So this is the time view of the processes, and we can see how when a single process is active at a time, process A has to be evicted from the processor. That's when the process B starts and runs until it's evicted. That's when the process C begins, process D, and round robin scheduler would say, well, if I'm done with D, I will go back to my process table, get the first task that is queued up and ready, and I will start executing again process A, then B, then C, and this round robin evicting and placing processes into the processor. So advantages of the problem of the multiprocessor is the parallelism. It is a kind of a notion, but it's also a pragmatic use of running multiple processors in a memory. So it's very desired and beneficial for the users. That said, there is still plenty of systems out there that are not concerned with making multiple users or single user happy with running multiple processes. Systems are designed, for example, big throughput jobs are designed not to run multiple processes, but to maximize the computational throughput of a system, in which case it's a single process loaded onto a single or multiprocessor, and then executed for a very long time until we get results. So can you think of different processes that would be optimized for throughput rather than multiple processes running at the same time, which would be optimizing on parallelism? So think about, well, I'll give you one: modeling. So if we want to do a weather forecast, we do not really care if we are playing Tetris or Doom at the same time as we are doing model prediction, crunching data on the weather forecast. We want to just run that single weather forecast model, crunch the atmospheric data, and in this case we are strictly concerned with the computational throughput of this single task. Thus a dedicated kind of a batch process where we are maximizing the time on the processor rather than multiprocessing or parallelism of multiple processes is not a concern. So every kind of advantage also has its inherent disadvantages. So here's an example of having two programs. So here's a program 1 that is doing nothing other than repeating and gets assigned increment n+1. And problem B it's repeating a code which prints n and then resets it to 0. So if we have these two processes or programs, if they are not in a processor, we'll call them programs. The moment we take a program, place it in a processor, it's being executed, we call it a process. Then when it's offloaded, it's back to being a program. That's a good way of distinguishing between program and a process. So many times the execution of these two programs concurrently as a processes is not reproducible. Just because we do not have that fine of a control, unless we are a scheduler, and scheduler is owned by the kernel, we do not have the control when we will kick out program A and put program B into the processor for processing. So the actual execution can be kind of out of whack. So one scenario is where we would execute n equals to n plus 1. So that's the code from program A. And then program B would run on the processor. So we'll print n and reset it to 0. So then the output would be n plus 1, and then 0. The second scenario would be where program B would get to the processor first. So we will print n, set it to 0, and then increment n. So we will have 1. So the actual output would be printed n, whatever the value is. We'll reset it to 0, and then the increment happens. So final scenario is when we have the instructions from the program A kind of interwoven with the instructions from the program B. So we will take the first instruction from program B, then the first instruction from program A, then the second instruction from problem B. So you can see here, if we have one shared variable n between two processes as a shared memory, we really have to protect this memory so it is consistent. It's not kind of, the computation is not interrupted kind of in the mid-flight, and we will, every single time we run these two programs concurrently, we will have consistent results. We should not get inconsistent results based on basically different results every single time we run it, and the result will be dependent how the processor scheduled these two processes in memory, in the processor for computation. So another example for these kind of troubles is different processes have different time requirements. So some are heavy on the processor time, some are heavy on the I/O. So the ones that are heavy on I/O, they actually spend a lot of time waiting around until the processor becomes available, because what they are doing while waiting, they are getting their data. So then they spend a split second in a processor, and then if they require more I/O, then they basically evict themselves from, or a good scheduler would evict them from the processor, say, all right, you need to wait for your data, so why don't you just wait for the I/O to return? When you're ready, let me know, and I, as a scheduler, put you back into the processor. So once again, analogy for making the fine difference between a process and a program. So if you're actually doing something like baking a cake, you are a process. But then if you get a request from your crying son, then that's a program that needs attention in a processor. So that would be a program, because it's not currently loaded in the processor. So that's why it's a program. And this is where kind of the differences between processes and threads will start getting very, very apparent. So to give you the punchline, so far we were forking off processes, which is very, very heavy request on the kernel. So the kernel has to do a lot of bookkeeping to create a new process. So it has to create basically a stack frame. It has to establish the file descriptors, IOs, global variables, and so on and so on. It has to request a slot in the scheduler, and so on and so on and so on. So that's a very expensive operation from the operating system in terms of time. So if you are creating a process, be sure you want to keep it around for a while. Threads, on the other hand, are a lot cheaper and a lot faster to instantiate. They share a lot of memory space and a lot of, for example, file descriptors with the parent process. They are much lighter. So many times you will hear heavy process and light process. So the light process is most likely referring to a thread, and heavy process is referring to a process just because it's a lot of overhead on the kernel to create a process, low overhead on the kernel to create a thread. So the threads are still subject to be scheduled, but they are kind of loosey-goosey. So they share a lot of memory, they can stomp over each other. Processes are nicely separated from each other. It's hard to share memory between them, so that's why we are passing signals and messages between the processes to accomplish inter-process communication. In threads, it's much easier, much lighter, but it also creates some challenges of now a variable can be accessed by 2, 3, 4,000 different threads at the same time. So we better protect that shared resource, in which case it's a shared memory. So we'll see the process creation details in a little bit. We did talk about how a process talks to a kernel through interrupt, and we will now see the other side of actually creating a process, inserting it into a schedule queue, and servicing different requests from the operating system or from the user. In the other tutorial on the signaling, I also showed you an example how an operating system can talk to the process through signals and through a service handling requests. So, instantiation of a batch job. So the process termination, which is basically terminating or killing a process, can be twofold. It could be either voluntary or involuntary. So if you are returning a value, it means that you will voluntarily exit, which is a normal termination of the code. Also, you should be checking kind of error checking for any kind of call, memory allocation, system or procedure call, or if you fail to do something. So once you catch the error and you exit because of the error, there is also voluntary. You did check for correct execution of the code. It didn't work out well, then you exit it, which is on error, but it's still voluntary. Fatal error is something involuntary, so your code basically crashes. Many of you have seen or experienced segmentation fault. Basically, you started to dereference, for example, memory that you do not have access to or that doesn't exist, in which case your kernel would say, nope, you cannot do that, and I'm going to kill you. And in that case, it core dumped because the kernel said you are not allowed to do that, so it terminated involuntarily the process that was trying to do ugly things to the memory. And finally, other processes can kill processes that they do not like to run, or they need to terminate externally or from the outside. So that's also involuntary because the signal does not come from the process, but kind of process within. But other process called the kernel and said, I would like to terminate this process that I do have access to. You cannot just go and terminate somebody else's process unless you are a super user. So I'm gonna go and request that kill signal to be sent to the process. And once again, the signal code video will show you that from a command line or from a standard in, you can request a process to be terminated by sending in a signal. Control-C for interrupt, Control-Z for stopping the process, Control-backslash for termination, and so on. And so Control-D is end of file. So if you have a non-terminating input, you can always send a signal Control-D, which basically sends end of file marker to the standard in, and that's gonna terminate the input. So those are different termination of your code. So here is what a program can be what can be the state of a program. So once we create a program that is loaded into memory, it is running. So a program in the memory can have kind of two things can happen to it. The first thing is it will kind of have to wait because it requested some information, so I/O, memory read or disk read, of information that is not readily available. So a program will block itself saying, all right, I need to wait for the input. There is no reason for me to stick around in the processor and be blocking the other processes that can be running while I'm waiting for my I/O. So it will kick itself out of the processor, then puts itself into state blocked. And once the I/O arrives, it will have the information for processing, so it can switch itself into a state ready. So input becomes available. Now I'm ready. So I'm telling the scheduler, yes, you can put me back into the processor. The other scenario is when the process loses its time on the processor. So you have a time slice. Let's say you're allowed to run for 20 milliseconds. Your job takes you 30 milliseconds, but that's irrelevant. So after 20 milliseconds, you get kicked out of the processor. You get sent back to the scheduler queue. You are still in the ready state. And when it's your time again, you will be put back into the processor because other processes had their own, other programs had their own term on the processor. They get done, it's your turn again, and you as a process in the ready state being included in the scheduler gets placed back into the processor, and now you are being executed. So this is a very solid interpretation of what the processes do when they are, or what is their state other than running or ready or in this case blocked. So here is kind of a more detailed view. Anytime I'm creating a process, I'm going to insert it into a process table that is accessed by the scheduler, and the scheduler kind of walks through this table in some fashion. So if we have a round robin schedule, the scheduler will just go from the process entry table 0 to process entry n -1 and just keeps on going, pulling the processes out of the table, putting them into the processor, placing them back, kind of evicting them, and just keeps on going until you pretty much shut down the computer. And here is the ugly side of implementation of a process. So we have, well, teaching this class on operating systems. Some people teach it in 3 blocks. They teach it as a processes, memory, and a file system. Well, that's exactly what is happening to any process that is being instantiated. So first we have to create a process in terms of the process management. So we have to give it registers, program counter, status, kind of what status is the stack frame in, stack pointer, priority, process ID, parent process, so who called it or who created this child process. So everything is a child process other than the kernel. Who the process group this process belongs to. Many times this is inherited from the user that is instantiating the process. Signal handling routines, when it was originally started on or inserted into the process table. So that's going to give you the uptime of the process, so you know how long it was running for, how long it's spent actually in the CPU, its children, and when is the next alarm thrown or attention request. So the memory management also tells you basically where on the stack you are, what is your text data segment and your stack segment information. And from the pipe programming sample video, I already showed you that each process instantiation also comes with a file management. So the root directory, working directory are also inherited from the parent. The file descriptors are created as kind of a local global copy of, and then user ID and a group ID. So this is some of the fields. This is not an exhaustive list of all of the process bookkeeping. So you can see this is a lot of work if you are a kernel. This takes a lot of setting up to do. So this is kind of where you want to tread lightly and choose wisely between, oh, do I want to fork off a new process or create multiple threads that are, but then I have to deal with the threads kind of synchronizing or sharing the same memory. So from the kind of a higher level of the process implementation, we have the hardware stack program, we have the load of the counter and interrupt vector, assembly language procedures, saving registers. So this is kind of necessary for the context switch of the different processes. So then there is the C interrupt. So we need to be able to somehow externally address the processes when they are running. So that's where the C interrupts come in, and they are definitely for the reads and the I/O, so the input side, so buffer input. Scheduler will kind of puts it into the table and assigns its priority and time slice, and many of the schedulers are not pure one method, so they usually have some implemented heuristics that is doing kind of a multiple of different algorithms implementation of the scheduler routine. And finally, we do not just want to have the read C interrupts, but also the returns. So if this process terminates, where is it supposed to return its return value to? So that's we have seen this already when a parent was creating a child, and the child was returning with the exit value, and somehow magically parent caught that return value. So that's actually done by the kind of the higher level process instantiation, the return address. So when the child is created, it knows where it should write the return value to, so whoever called it can retrieve it. And then kind of some additional bookkeeping if you want to create a new process. So we can fundamentally look at the programs in terms of what are their tasks. So if the tasks are mostly crunching numbers that just needs 5 meg table, then it is a processor heavy process. If we have a program that is mostly reading information from a disk, processing it, or searching for a phrase, that's very I/O heavy. All the program is doing on the processor is doing basically string compare, looking for a value. Well, most likely it's not gonna be there, so it's gonna dump the value that it just read from the file and try to read a new one. So those are very I/O heavy. So here we can see the disk utilization, the CPU utilization with respect to the degree of multiprogramming. So we can see that the processes that are only 20% I/O heavy, they kind of reach maximum processor utilization very quickly on kind of a 2 multiprogramming kind of a degree. So the more heavy, it will take a lot longer to reach the high CPU utilization, because most of that time is spent waiting for the I/O. So that's why the time in a CPU is very slowly climbing. Something that is not waiting for the CPU, for the I/O, kind of utilizes the processor much faster. So in summary, we kind of covered fine details of how the parallelism is achieved, but also the differences between a process and a program, looking at the process creation, and implicitly we also then had to cover process termination. So not just how we can interrupt or kill the processes, but also we talked about creating the processes. Well, the moment the process is killed, that memory, that stack frame has to be deallocated and returned to the operating system. So if it takes a long time to create, it does take quite a bit to reclaim that memory as well and return to the operating system. And we talked about the different perspective on the processes, whether or not they are kind of a number crunching heavy or they are the I/O heavy, so they have to do a lot of read and writes, and that kind of gives you some impetus to analyze what is your processing task like, what does it take most of the time.